Hi, this is Mrs. Marquette, and today we're going to talk about solving quadratic equations, specifically with some square roots. Before we start actually doing some solving, we have to review just a couple of things. The first is what really is a square root. So if I give you 4 under the square root sign, you would tell me that the square root of 4 is 2. The real reason that is because I have 4 written as 2 squared. So 2 squared is 4. And then this square root and my square really undo each other. Okay, they're like inverse operations, kind of like adding and subtracting or multiplying and dividing. My square root can undo a square. My square can undo a square root. So when both of those cancel out, I just get 2. But then really, what does a square mean? Well, 2 squared means 2 times 2. So what we'll say today is that if we get a pair of numbers or a pair of variables, that's really that number squared or that variable squared. So that pair can undo my square root. So those are kind of the 2 ways we'll talk about square roots today. That if I have a square, I can undo the square root, or if I have a pair, I can undo the square root. The other thing that we need to review is a prime factorization. And my prime factorization really is if I take this number, think all the way back to like middle school, I want to find 2 numbers that multiply to 24. That could be 12 and 2. It could have been 6 and 4. But I can keep going until I can't break down any of my numbers anymore. So 12 and 2 could be 6 and 2. 6 could be 2 and 3. But then every single one of the ends of my trees can't be broken down anymore. So 24 can be written as 2 times 2 times 2 times 3. That's written down all the way to its prime factors. So we'll do one more of these together. 32 I can write as 8 and 4. 8 is 4 and 2. 4 is 2 and 2. 2 and 2, notice I only look at the ends of my branches here because if I also counted the 4, I'd be double counting. So I've got 2 times 2 times 2 times 2 times 2, and that's the prime factorization of 32. This last one, number 15, breaks down pretty simply to 3 and 5. Can't break either of those down anymore. So our prime factorization is 3 times 5. So now we have reviewed square roots, we've reviewed prime factorizations, we can go to work. The property of square roots that you'll have in your guide for your test, the real big theorems today, is that if I have a product of 2 numbers under the square root, I can break them up, or if I've got a product of 2 square roots, I can put them together. So I can break up or put together. And then the quotient property says that if I have a fraction under a square root, I can say the square root of the numerator, or the top, over the square root of the denominator, or the bottom. So let's see what this looks like. I've got 24. Notice this is exactly the same problem we did before. I want you to break this up all the way down to its prime factors. So we did before 12 and 2, 6 and 2, 3 and 2, and let's rewrite this under my square root as 2 times 2 times 2 times 3. Thinking all the way back to the very beginning, when I have a pair, when I have 2 of one number, they can undo the square root. So I can rewrite this, or I can look and say I've got one pair right here, and I can rewrite this as 2 times 2 under a square root and 2 times 3 under another square root. In the next problem, we won't do this middle step, but I want you to see that this 2, this pair of 2's, can become just a 2. And then 2 times 3, I don't have any pairs, so I'll just rewrite that as 6. So my final answer is going to be 2 times the square root of 6. Number 2, 500. I've got to break this big 500 down. The easiest way I can think of is 5 and 100. 100 is 10 and 10. 2 and 5, 2 and 5. So rewrite that all under our square root. I have 2 2s, I have 3 5s, and let's circle some pairs. I've got a pair of 2s, I've got a pair of 5s, and then just one leftover 5. So my pair of 2s will undo the square root and come out. My pair of 5s will undo the square root and come out. And what's left over is a 5 under the square root. Final step. I can actually multiply those two numbers because they're just two numbers multiplied together. That is going to be 10 square root of 5. The biggest thing I can tell you on these problems is really break them down all the way and then go ahead and start circling your pairs. It'll really help, especially as you're starting. So that's like number 3 here. I'm going to break down everything. So 6 is 2 and 3, 15 is 3 and 5, and then because of our product property, when I have two numbers that are in square roots, I can put them under the same square root. So here I can say I'll put 2, 3, 3, and 5 all under that same square root. I've got one pair. That one pair can come out, and then 2 times 5 is under the square root. Final step is always going to be put together whatever you can. The 3 is on the outside times the square root of 10. Number 4 is similar. I've got 12 that I've got to break down. I've got 6 that I've got to break down. Notice that I don't break down the 3 because it's not under a square root. It's just going to hang out with us on the outside until the very end. So 12 is going to be 6 and 2, or 3 and 4. 6 will be 2 and 3. Again, 6 will be 2 and 3. So here are all of the ends. So this is equal to 3, and then under the square root, I've got 2, 2, 2, 3, and 3. I always put my numbers that are like together because then I can see that I'm going to circle some pairs. You don't have to do that, but I think it helps. So notice that I circled my pairs. The 3 stays, and then I bring out a 2 and I bring out a 3 because my 2 squared and my 3 squared will each cancel the square root. And then my leftover is going to stay put. Multiply all of these numbers. 3 times 2 is 6, times 3 is 18. Square root of 2. So that's when we've got multiplying. The next thing we've got to deal with is when we have a fraction. So to be considered a simplified radical, I can't have any square roots or radicals in the denominator. The denominator means the bottom of the fraction. So if I look at number 5, the reason that this isn't simplified is that I can break it up as radical 7 over radical 16 because of this property, the quotient property. And then I can simplify these square roots. 7 I can't break down, so I'll leave it. And if you need to go and do some side work and break down 16 into 4 and 4 and keep breaking it down like a tree, that's totally fine. I actually can see that I know the square root of 16. It's just 4. So since I already know that, I can just break it down as it is. And then this is actually simplified because, again, to be simplified, I cannot have any roots in the denominator. I don't, so I'm done. Number 6 is a little different. When I break this up into square root of 7 and square root of 2, I still have a radical in my denominator. I can't break down 7, I can't break down 2, so I've got to do some work. What I would really like is I would really like to have a pair in the denominator. I'd like to have a 2 and probably another 2 as well. So what I'm going to do is I'm going to multiply by a square root of 2 on the bottom. Reason being, I can look ahead and see, okay, that means I'm going to have 2 times 2. That'll be a pair on the bottom. But I can't just multiply by something on the bottom and think that that's going to be okay. If I multiply by something on the bottom, I also have to multiply it on the top. So now really I'm just multiplying by 1, which is fine. and I can go to work. So I've got 2 times 2, and then I've got 7 times 2 on the top. 7 times 2 is 14. There were no pairs for me to circle, so that's fine. And then I've got my pair on the bottom. I've solved the problem of my radical in the denominator, so radical 14 over 2 is my final answer. Number 7 is going to be very similar to the last one, only before I start, I noticed that radical 25 over radical 3, I already know the radical of 25. The square root of 25 is 5 over radical 3. If you didn't see that right away, that's fine. We can still break it down later. But now I'm in the same place as the previous problem. I don't like that I have a radical in the denominator. I would like to have another radical 3 so that I can circle my pair and get rid of that radical. But then I have to multiply by a radical on the top. So on the bottom, I get radical 3 times 3. And then on the top, when you have a regular number without a radical, it multiplied by a radical, they're not two things that you can multiply. So I can just squish them next to each other. So remember, like with variables, when we put variables next to each other, that really means that you're multiplying them. So on the numerator, I've got 5. Rad 3 is how we can say that, or 5 square root of 3. On the bottom, I have a pair of 3's. This is my final answer, even though it looks kind of funny. See if you can do that number 8 in about a minute. I'll have you check that. So here's number 8. We have rad 22 over 11. You had to multiply by rad 11 over rad 11. So double check your work, and if you've got questions, rewind the video and look back at the last two, because number 8 should be pretty similar. So that's kind of what we got for our first video. Again, properties of square roots. You can split up products. You can split up quotients. In the next video, we're going to talk about how to solve problems that actually have square roots in them.